The MIWA U9 is a lock developed, manufactured, and sold by MIWA Lock Company, a Japanese lock company. Its original patents were published in 1982, and the product began selling to the public in 1991. MIWA referred to the lock's mechanisms as the rotary disc tumbler mechanism. Let's first examine the key. The key bow has the MIWA logo on it, along with its key code. The blade has cuts on both sides, kind of like this old wafer lock key. But unlike this cheap wafer lock key, the key cuts are asymmetrical. We can find out why by looking at the lock itself. The keyway is shaped like the alphabet W. This prevents the key from being inserted in the wrong way, only allowing the intended orientation. The key works fine when inserted. The lock can turn freely 360 degrees, and the key can be taken out when the core is oriented to the original 12 o'clock position. The outside parts don't have much to look at, so let's take this lock apart and see the internal components. We can first pry off this metal ring on the back with something flat. I'm using my circlip pliers for convenience. Removing this enables us to freely remove this outer part and a big spring that interacts with it. Under the metal ring, there also is a black circlip that holds the core from coming out. Removing this using a circlip plier reveals a metal washer. We can also take this out. Doing that allows the whole core part to slide out from the outer metal housing. The real core is inside this other black housing. Let's shortly examine this core before we take it apart more. Seeing the core from the keyway side, you can see that the core housing is not a perfect circle. Instead, it has a small groove that extends outside. In that groove, there is a metallic component. This metallic component is called a sidebar, but we will look more into this part after we take the core out of the housing. At the back of the core, there is the tailpiece, 2 screws, and a C-clip that holds it in place. You can either remove the 2 screws to take out all of the tailpiece, or just remove the C-clip. For convenience, I'll be removing the C-clip to take out the core. Removing the C-clip allows the tailpiece and a washer to come off. After that, you can take out the whole core by inserting the key and rotating the core. If you are planning to try this by yourself, I suggest that you push and hold the sidebar while pulling out the core. The first thing we can notice is the sidebar. This is how the sidebar looks. Let's examine a bit more closer. The upper side is a flat with a small notch in the middle. The bottom side is thinner than the upper side and has these 2 small protrusions. If we return to the core housing, we can see that there is a small metal plate that goes through the center part of the groove in the housing. This metal plate protrudes inside the core and the notch in the upper side of the sidebar catches this protrusion. This allows the core to not slide out when the core is in its idle orientation. Returning to the sidebar, you can see that there are two springs on the core and they match with the two small protrusions on the bottom side of the sidebar. The springs always push the sidebar to the outer direction of the core, therefore the sidebar rests at the core housing groove. Removing the two springs reveals the actual core. We will take this apart more, but let's try using the key first. As you can see, there are some metallic parts that are moving while the key is being inserted. These moving parts are called levers. They correspond with pins in a pin tumbler lock. These levers are what prevents the lock being turned at its idle orientation. You can see that this side of the levers are not smooth. There are some ledges and shallow, deep cuts in it. When the key is fully inserted, you can see that these deep cuts perfectly align into a single line. When in this state, the bottom side of the sidebar, which is thinner than the upper part, fits perfectly in this single line. Let's examine how the core turns when the correct key is used with the information we found out. We've recreated the main core of the lock in 3D for a better and effective demonstration. We've also printed the same model but with a bigger scale than the original lock using a 3D printer. I'll cover that later in this video. The left side is a rendering of the lock core when the key is being inserted, and the right side is a cutaway version of it. You can see that the levers are being pushed by the key when it is being inserted, and the amount of the levers being pushed is determined by the depth of the key cuts. If the key is inserted and all the levers are moved into their desired states, the cuts line up into a singular groove. This makes room for the sidebar to come in, but the sidebar is currently being pushed outside from the core by these two springs. It is resting inside the core housing groove. If you look at the sidebar at this side, you can see it has slopes on both sides. It is shaped like a small house with a reverse V shape on the top. This slope is pushed at the sides of the core housing groove when the core is turned, and the sidebar is retracted inside the core. The sidebar is normally prevented from being pushed in since the levers are in the way and there is no room. But when the correct key is inserted, there is now room for the sidebar. So when the core is turned with the key, the sidebar retracts into the core successfully. After that, there isn't anything preventing the core from rotating, so the core moves freely. Now we know the basics of how this lock works. Let's dig in a bit deeper and take apart the rest of the core too. Normally, this keyway plate is crimped on both sides at the factory, but you can pry it open. I've taken it apart a few times so it comes out pretty easily. You can already see one side is sticking out. After taking off the keyway plate, you can see how the levers look like. This is the U9 lever. It looks like a U when you look at this side. There are a total of 9 levers on this lock, hence the name U9. At this side of the lever, there are 2 holes. One hole is for the central core rod that you can see here. The other holds this small metal strip. This strip acts as a spring. At the other side of the lever, you can see the ledges, shallow, deep cuts we saw earlier. The deep cuts are the true gate, which allows the sidebar to retract. The shallow cuts are the false gate, and as you can tell from the name, these are literally false gates, and they exist to make picking this lock much harder. The false gate is shallower than the true gate, therefore the sidebar cannot fully retract into the false gate. All 9 true gates have to be aligned in order for the sidebar to retract successfully. Finally, this side of the lever is the part that interacts with the key. The lever is pushed by this side when the key is entered. Without the key, the spring pushes the lever back to its place. After a lever comes a spacer. It's just a funny looking metal plate with holes, and as the name indicates, it only serves as a spacer between 2 levers. You can see that the keyway hole is also on the spacer. It basically aligns the key when entered. Another lever, another spacer, and another lever. This third spacer looks a bit thicker. It's because this spacer has this hole on its top, which holds one of the two sidebar springs. The other spring hole is at the end of the core frame, right here. Other than that, taking apart the core is basically the same process. One lever after one spacer until all 9 levers are taken out. You can see that there are 2 metal rods that go through the center of the core. One holds both the spacers and the levers, the other rod only holds the spacers in place. While taking out the levers, you should have noticed that the levers were not placed in the same orientation. Some are flipped compared to the other levers. If we examine the 9 levers that we took out, you can see that the gates are all cut differently. These differences match with the cuts on the key. Coming back to our key, we can see there are a total of 9 cuts on this key. As you saw, some cuts are on the one side of the key and the rest of the cuts are on the opposite side. This interacts with the lever placement, therefore allowing 2 different orientation of the levers when assembling the lock. 5 different key cut depths are available based on the location of the true gate on the lever. Each lever could be placed either left or right, and there are a total of 9 levers. So in total, there are up to 1 billion possible key biddings. Before we finish off, I'll have to show you the 3D printed version of the lock that I've mentioned earlier in this video. It is based on the 3D modeling that we've created. The tolerances of our 3D printer were not perfect, so we had to file and trim down many parts to make it work. We used brass rods as the 2 core rods and small plastic strips as the lever springs. As you can see, it's a bit stiff, but works just like the original lock. The levers move when the key is inserted, and the true gates align perfectly. And that's about it. This concludes about the U9 for now. I personally think the U9 has a really unique mechanism that differentiates itself from other ordinary locks. Every part of this lock is designed and made very well. I can admire it all day. And watching the levers move while the key is inserted is very mesmerizing in my opinion. I'd like to give a shout out to some special people before we finish. First, Rain, who helped me find people that can review my works. Correct Jeans, who kindly read my initial script of the video and gave great feedback. Alpama, who also read my script, gave feedback and pointed out grammatical errors. And finally, all the members of the Lockpickers United Discord. Without the support from you guys, this video would not have been possible. Thank you so much for watching, and have a great day.